Okay, so let's get started. So today we're going to discuss two more predictions of linearized gravity. Okay, and so it's already quite surprising, right, that we've got a number of interesting results just from the linearized version of this theory. Okay, which is an approximation to the full general relativity. But all these linearized approximations, they actually give you some insight into what happens in the full general theory of relativity. Okay. So it's just that these solutions are much simpler to work with, these approximate solutions. So what we'll do next is today we'll study these two types of effects. One are the so-called gravimetric and gravomagnetic fields. Okay, or this is called GEM theory. Okay, or gravo-electromagnetism or gravito-electromagnetism. Okay, it's a gravitational analog of the laws of electromagnetism that emerges in the linearized gravity limit. Okay, this emerges in the limit that you don't neglect the velocities of sources completely. Okay, you keep it to first order. Till now, in our approximate calculation where we showed we recovered Newton's laws, we neglected the velocities of the source and we neglected the velocity of the test object. Okay, we'll restore the velocities of the source and the velocities of the test object, at least to first order and velocities v by c. First order and v by c, we'll keep terms like that. Okay. And the next thing that we'll see is the prediction that you can also have gravitational waves. Okay, this you might all know is one of the biggest discoveries in the last decade, and it's in fact it's not just a discovery that we've discovered gravitational waves. It's opened a completely new window into astronomy and astrophysics by allowing us to see things like black hole mergers, black hole neutron star mergers, and possibly even things dating back to the Big Bang. Okay, so there's a lot of future in this field of gravitational waves, so I'll spend some time talking about it. Okay, so let's talk about GEM first. Okay, so we considered corrections to linearized gravity where T mu nu, as I mentioned earlier, was just of this form. Okay, we just taken rho, and we had considered the fluid to be static. Okay, so every component of this fluid was static, and rho was therefore conserved with time, and we basically solved or we derived the linearized approximation, and we found Newton's laws in that case. Okay, but now what we'll do is we'll consider that each fluid element can now have a small velocity v. Okay, so this v can be dependent on x and t. That is, different fluid elements can be moving with different speeds, so the fluid can flow. Okay, so T mu nu we'll just consider it to be of the form rho times u mu times u nu. So we're still assuming that it's a pressureless fluid. Okay, so it's really like dust. Okay, but it's basically just particles moving around. So this u mu is approximately, in the approximation that we're working in, you can just take the non-relativistic approximation for full velocity, which is 1 in this component, and v bar, okay, for the other three components. So that is u mu. Okay, and this, just remember that this u mu can now be a function of x and t, like different components of the fluid at different places and at different times can have different velocities. Okay. Okay, so what happens to T mu nu then? Well, T mu nu, if I just plug in this expression for u in here, right, what I would find is something like this. It's rho v bar on, so this is, for Vx, Vy, Vz, this gives me a column. Okay, this gives me one column here. And now this is a 3 by 3 block of T mu nu that's sitting here, and it has entries rho times Vi times Vj. Okay, now what we're going to do is we're going to ignore terms of order V square. Okay, so we're only going to keep terms linear in V. So if we make that approximation, then our stress energy tensor basically has this form. Okay, it's rho here, rho V bar. Okay, this is the first row, and this is the first column. Okay, rho V bar along this column. And this 3 by 3 block is 0. Okay, so in other words, what you'd say is this part is called the stress. So we say that this stress is 0. Okay, there are no stresses and there's no pressure. Okay, but there's only flow, okay, of these particles. So now what we'll do is we'll define a current, a forecurrent J mu, which is rho and rho V bar. Okay, and we'll write this as rho, and we'll write this as j bar. Okay, so rho v bar we've written as j bar. So now rho can be a function of x and time, and j can be a function of x and time. Previously, the continuity equation told us when the velocities were 0, that rho doesn't change at a particular location. That is, rho is only a function of x. And the reason this was the case was because if you have continuity of the fluid elements can't just disappear. Since they're not flowing anywhere, they remain conserved at whatever location they are. The density stays the same. But now that you have velocity flows, okay, rho will be a function of x and time. So let's see how that works. Okay. So if we look at the conservation of the stress energy tensor, the stress energy tensor conservation equation is this. Okay, and so we want to work it out to leading order. T mu nu is already a first order quantity in the perturbations. Okay, so we'll write this as partial mu T mu nu is 0. Okay, so this del mu will just keep the leading order piece. We'll ignore the connection. Okay, the Christoffel connection, which is a first order piece. Okay, so we get partial mu T mu nu is 0. Okay. And let's take the nu is equal to 0 component of this equation. That is partial 0 t0 0. I'm just writing out the summation over mu explicitly by splitting it into spatial summation and sum over time. Okay, it's partial 0 t0 0, partial I ti 0. I've taken nu is equal to 0. Okay, and so now if I plug in t0 0 is rho. Okay, and t I0, which is the same as t0 I because T is a symmetric matrix, is J. Okay, so what this gives me is Ji. So what this gives me, if I write it out, is partial T rho plus del dot J is 0. Okay, so you see that the continuity equation really implies, or this equation, this conservation of the stress energy tensor, sorry, this one, right, is really in this limit. It's really telling you this is the conservation law. This is the usual continuity equation, which tells you that if you're in a region, you have some density. The only way that density can change is if there's an outflow of some current. Okay, you might have seen this maybe in the case of quantum mechanics if you've not seen it in a fluid mechanics class, right, where rho is interpreted as a probability density. Rho is like mod psi square, and J is something like I times psi star del psi minus psi del psi star. It's a flow of probability from one region to another. Okay, so have you all seen this equation before in that context, in the context of quantum mechanics? Yeah, so probably in the first course on quantum mechanics you would have taken would have covered this. Okay, so this is a more general thing. It's seen for fluids. It's seen in many other places. Okay. Okay, so now let's plug in. Okay, this stress energy tensor, this one here. Oh, sorry, this one here. Okay, we'll plug it into our linearized Einstein equations. Okay, and our linearized Einstein equation was just this. Box h bar mu nu is equal to minus 16 pi gn t mu nu over c to the 4, where box was this wave operator. Okay, and remember that we're using the signature minus 1 1 1 1. Okay, so box in this definition has a minus sign for the minus partial t square. Okay, so now for if you take the mu nu is the ij components of this equation, tij is 0. Okay, so these are source free equations, and with the appropriate boundary conditions you can set this to 0. Okay, h bar ij to 0, and this satisfies this equation. Okay, so we'll assume that h bar ij is just 0, and now what we want to work out is the other components of h bar mu nu. Okay, that's all this equation. So in particular we are solving the equations where at least one of these components is not a spatial index. Okay, so we're solving for h bar, let's say 0 mu. Okay, and since h is symmetric, or h bar is symmetric, h bar 0 mu is the same as h bar mu 0. Okay, so we have to solve this equation. And this equation is box h bar 0 mu is 16 pi g t 0 mu. Okay, so there's something slightly subtle, okay, about this change. This minus sign became a plus sign when I raised the indices. Why? Sorry, summation over? Yeah, so what specifically is the step that gave me that minus sign? What index? I raised two indices. I raised the 0 index and I raised the mu index. Yeah, so see the mu index I've raised on both sides. Okay, so that doesn't change the sign. Okay, but the zero index is not a summed index. Sorry, it's not a free index. Okay, that's a particular index that I'm raising. So what I'm really doing is you have to think of it as, let's say I multiply by this equation by eta 0, 0. Okay, that's what would really raise this index. Or really, if I go back to this original equation, if I want to raise this mu index, I'm multiplying by eta mu prime mu and taking mu prime is equal to 0. Okay, so only the mu is equal to 0 contributes, and eta 0, 0 is -1. Okay, and so therefore I will get this law. Okay, with the plus sign. So now what I can do is I can write this box h bar 0 mu. This t0 mu is just a call. Okay, this is just this column. Okay, t0 mu is just this column. Sorry, this row. Okay, it's rho v bar. So this I can define as j mu. Okay, where j mu, we have already defined it as rho and rho v bar. Okay, I can think of it as a column or a row, doesn't really matter. Okay, this h bar 0 mu is now defined as -1/4. Okay, u and ag. Okay, so this a is going to be like the electromagnetic vector potential. Okay, the 4 vector potential. But I'll put the subscript g just to remind us that this is a gravitational object that we're talking about. It's not something in electromagnetism. Okay, so ag is the symbol and it has an index mu. So if I make the substitution and I plug it in here, then the equation that I get is box a mu g is equal to -4 pi j mu. Okay, I've also set gn to 1. Okay, we can restore it if needed. All right. So now our gauge choice, we also had made a gauge choice earlier, which is that we had used this gauge, which is the analog of Lorentz gauge. We use partial mu h bar mu nu is 0. Okay, and in that choice, again, if we take the nu is equal to 0 component, this is the choice that we've made. Okay, by the gauge freedom, which is we are free to choose the make a coordinate transformation such that this is true. Okay, and once we make that coordinate transformation, so if I write it now in the language of this A, okay, this was a definition. Okay, that gives us this condition: partial mu a mu g is 0. Okay, so I have this equation and this condition. This is the gauge condition. But this equation is very similar to the equations in electromagnetism in Lorentz gauge, right? In Lorentz gauge, you have exactly these equations. Box a mu em is -4 pi j mu em, where a mu is the electromagnetic vector potential. Okay, j mu is also rho j bar, but rho is not the mass density or the energy density. Rho is the charge density in that case, and j bar is the current density in that case. Okay, so that is j mu em. And we also have this condition, which is called the Lorentz gauge condition. Okay, where and this a mu em, the 0th component of this is phi, which is the scalar potential, and this a bar is the vector potential. Okay, and our electric and magnetic fields are defined in terms of these as minus del phi minus partial a partial t and del cross a. Okay, have you all seen this in the intro E&M course, the first year E&M course you had? Right, you've seen electric and magnetic fields defined through this vector potential, right? Okay, so 4 times. Where? No, it's 0. Oh, sorry. Yes, it's -1/4 of this is equal to a mu. Thanks. You're right. Thank you. Yes. Okay. So with this transformation, right, we see that the equations, the sourcing of the okay. So first of all, you can source this a mu gravity, okay, from a flow current, where this flow current involves rho and rho v bar. Okay, it's an energy density and the flow of energy density. Okay, so just like you had a charge density and a current density sourcing electric and magnetic fields, now what we will find is that a mass density and a mass current, that is a flow of mass or energy, they can source what we'll call gravimetric and gravomagnetic fields. Okay, so this is the analog of Maxwell's equations. This first equation is Maxwell's equations. Okay, you can show that this equation is really just partial mu f mu nu is 4 pi j nu. Okay, maybe with a minus sign. Okay, it's because we're using a different metric convention. Okay, where this f mu nu, right, you can write as partial mu a nu minus partial nu a mu. So this becomes box a nu minus partial nu partial mu a mu is equal to minus 4 pi j nu. Okay, by our gauge condition, this is 0, and therefore you get the equation box a nu is minus 4 pi j nu. Okay, so really this equation is just Maxwell's equations. Okay, or at least two of Maxwell's equations. Okay, with the appropriate gauge condition. The fact that you had defined a mu itself, okay, the fact that you can write f mu nu like this automatically gives you the other two Maxwell's equations for free. Okay, the fact that you can define it like this tells you that there are no magnetic monopoles, for example. Okay, or there's no magnetic monopole current. Okay. All right. Okay, so basically there's an analogy between the linearized version of general relativity and Maxwell's equations. Okay, so that's really interesting. So if we go back to our linearized gravity theory, our metric is g mu nu is eta mu nu plus h mu nu. Okay, we solve for h bar. Okay, h bar 0 mu. Okay, and we've taken minus 1/4 h bar 0 mu is a mu, where a mu is this. Okay, so we'll define this as a mu graph. Okay, and this is some gravitational phi and some gravitational a. Okay, so it's the analog of what we have in electromagnetism. It's a gravitational scalar potential and a gravitational magnetic vector potential. Okay, so now I won't do this, but basically you have to write h mu nu. Okay, you can write h mu nu. We know how to relate it to h bar, right? It's h bar mu nu minus half eta mu nu h bar. So what you can do is you can work out h mu nu in terms of a mu graph. Okay, and then what you can do is you can use this h mu nu and plug it in here to find the full metric. Okay, so I won't do this step. I'll leave this for you as a homework exercise. It's a very simple step. Okay, so you plug it in here, and what you will get is g mu nu is of this form. Okay, this is the part that we had found before, minus 1 minus 2 phi, and 1 plus 2 phi times delta ij, which means on the diagonal it's 1 plus 2 phi, 1 plus 2 phi, 1 plus 2 phi. The new part that we're getting by not ignoring the velocities is this. Okay, we get minus 4 ai. Okay, this is very similar to what you would expect in electromagnetism, right? If you have static charges, you only get a scalar potential. Okay, if you have moving charges, then you get a vector potential which sources a magnetic field. Okay, so moving charges are a current, and currents produce magnetic fields. Okay, so so this is the form of the metric. Okay, so our so this okay, I hope the shorthand notation is clear. This is a 1-1 entry. These are the entries from or sorry, maybe I should say the 0-0 entry, and these are the 0i entries. These are the I0 entries, and these are the ij entries. Okay, sorry, which one? This one? No, it's 1 plus 2 phi. Yeah, because there's an overall minus sign, so you get plus 2 phi here, plus 2 phi here, right? Right, both of them have the same sign, right? In h mu nu, right? Okay. Okay, so now if we evaluate the line element, which is ds square, which is g mu nu dx mu dx nu. Okay, we see something interesting. Okay, it takes this form. ds square is minus 1 minus 2 phi dt square minus 8 ai dxi dt 1 plus 2 phi dxi square. Okay, so unlike what we had before, we now find that if you cover a dt distance and a dx distance, okay, and if your AI is non-zero, then that actually contributes something non-trivial to your space-time interval. Okay, this is non-trivial, right? This is something that we've not encountered before. Okay. So this phi is called a scalar perturbation and AI is called a vector perturbation, just like in analogy with electromagnetism. Okay, and this vector potential is causing this this new kind of mixing term between x and t. Okay. Now, what you can also do is you can find geodesic equations from this metric. Okay, so you can write down d square x mu d tau square is minus gamma mu nu rho dx nu d tau dx rho d tau. And if you have a slowly moving test particle, then you have dx mu d tau is 1 comma v bar. Okay, where v is the v of the particle now, not of the source. Okay, so this v is v of the particle. Okay, maybe I can put this p here to be explicit. Okay, so this is the velocity of the test particle. So now if we take the mu is equal to I components of the geodesic equation, okay, so now we look at this geodesic equation and we'll take only the spatial components, that is mu is I, not the time component. Then what we have is, okay, again, I'm not proving this, okay, you can work this out. D square x bar d tau square, what you will find is I've just multiplied the geodesic equation on both sides by m, okay, and here what I have d square x square d tau square is equal to minus m. What you'll find is gravitational E magnetic gravitational field also B grav, okay, times where this is a cross product with V of the particle. So V is dx of the particle times d tau. The gravitational field is defined, the electric gravitational field is defined as minus grad phi, and the magnetic gravitational field is defined as del cross E. Okay, here I've assumed that phi and A are time independent when you derive this. Okay, if you assume they're time independent, then this is the expression for E. Otherwise, you would have this extra piece. Okay, but we don't have this. Okay, this is the analog. Okay, so you see that this equation gives you the exact analog of the Lorentz force law. Okay, except there's this factor of 4. Okay, this factor of 4 you can't just define it away. Okay, because B is defined in terms of A mu. Okay, and you can't just get rid of it. Okay, so and this really comes from the fact that this is not exactly Maxwell's equations. Okay, or I mean, sorry, this is not exactly a spin 1 field. This is a spin 2 field. Okay, just from that fact, you get these factors of 2 just popping up here and there, or factors of 4 popping up here and there. Okay, so this theory. Okay, so now you have basically like you have Maxwell's equations plus the Lorentz force law, and that's the complete theory of electromagnetism. Okay, it tells you how particles move and how they source electric and magnetic fields, and it tells you how electric and magnetic fields act on particles which have charge. Okay, so this is exactly the analog, except that you have gravitational electric fields and gravitational magnetic fields. You have some factors of 2 or 4 sticking around, and the charge under gravity is m, it's not q, okay, like you have in the Lorentz force law. Okay, okay, so this is a theory of graviton-electromagnetism and it's called GEM theory. Okay, now I won't discuss the predictions in detail, I won't work out any predictions, I'll just tell you some of the predictions. Okay, you can look it up for yourself later. Okay, so one of the most important predictions is it predicts an effect called frame dragging. Okay, where if you have a source which is steadily rotating, okay, so imagine that you have, let's say this is the Earth and it's rotating. Okay, previously we have seen that if you are at different distances from the Earth, then clocks tick at a different rate. Okay, because the gravitational field is different. Now this gravomagnetic effect predicts something completely new. It predicts that if you have 2 clocks at the same distance, okay, so the R is the same, but now the Earth is rotating. Okay, now the Earth is rotating. So it's like in the problem in electromagnetism where now you have a charge and this charge is rotating. Okay, a ball of charge which is rotating. So the ball of charge which is rotating is produces a current, okay, and the current sources a magnetic field. In this case, you source gravomagnetic fields, okay, and so now what you will find is that in this co-rotating frame, okay, if you have a clock which is co-rotating, that is, it's rotating in the same direction as the rotation of the Earth, okay, such a clock will tick faster, and a clock which is at the same radius but rotating in the opposite direction will tick slower. Okay, so you will have a what is called a frame dragging effect. Okay, that is depending on your rotation speed, even if at a fixed hour. Okay, your rotation speed relative to the Earth, you will experience different rates of ticking of the clock. Okay, so this additional effect, this is an additional effect to gravitational time dilation, which is due to the scalar potential. This is purely coming from that magnetic vector potential that we talked about. Okay, so an experimental test to measure this is if you have light moving in the direction of the rotation. Okay, so if you have a light moving in the direction of the rotation, if you look at it from a distant observer's perspective, okay, that light which is moving along with the rotation will cover a greater arc length than light which is moving opposite the rotation. Okay, so it will appear to, in other words, light will appear to have different speeds along the direction of rotation versus opposite the direction of rotation. And this effect was actually tested by a satellite experiment called Gravity Probe B in 2011. And this effect was measured to within 10% accuracy, and it's in agreement with the predictions of general relativity. Okay, so it's not very precisely tested, but it's tested well enough that you can see this effect. Okay. Okay, any questions here? Yeah. Yeah, here. Yes. So all I did was multiply by eta 0, 0. Okay. I've just not made the eta 0, 0. Oh, I see. I should have multiplied both sides by eta 0, 0. So why is there a minus sign? That's a good question. Yeah, sorry, I don't think that it's, sorry, yes, there is no minus sign. Okay, so this is still a minus sign. And indeed, okay, this is defined like this. There's a minus sign here, and you get this equation. The reason I was slightly confused was in the textbook, okay, h bar 0 mu by 4 is defined as a mu, and therefore, sorry, this had a minus sign, and you can see that these two definitions are consistent. Right? Because if I raise the mu index, I have to, I mean, this definition and this definition and this definition are consistent. Okay, h bar 0 mu, one side only is multiplied by eta 0, 0 in this case. Right? Yeah, thanks for pointing that out. Okay, yeah, so indeed there is no eta 0, 0 here. There is still a minus sign here, and here I have a plus sign in the definition. Okay, and if you look in the textbook, you will see a minus sign here. So this discussion is basically following Wald again. Okay. Okay. Be a little louder. This one. So you have to be a little louder. Lorentz force law. This one. Because, okay, gravity is attractive, right? So the charges are yeah, so let's see. yeah, like charges will attract in this case, right? And they won't repel each other. Okay, so basically the sign of the force that you experience, right, is opposite to what you'd experience for like charges in electromagnetism. Right. So yeah, so that's another important difference in this gravimelectromagnetic theory, right, which is obviously different from electromagnetism, right? And that's what you expect as well. Yeah, thanks for pointing that out. Yeah.
We are taking fluids over here. Are we taking fluids just for the sake of getting more specific tensor, or like, we can say that it is actually the medium is actually like fluid?
Yeah. So okay. So this approximation of taking T mu nu as a fluid is a reasonable approximation. Okay. In the sense, for example, suppose you consider the sun. Okay. If you neglect the pressure in the sun, if you're averaging over large enough scales, it's just a cloud of density, okay, of mass density. So as far as the effects that you're trying to calculate go, okay, unless you're looking really into the details, even if you're looking at the details of rotation of the sun, as to the approximation that pressure is zero, the approximations we made are pretty good. Okay, for
Can we say that the frame drag that is happening is equivalent to the thing that happens because of viscosity in the fluid?
this is not really viscosity. Viscosity would occur in those VI Vj terms which we dropped, order V square. Um,
What we same for either fluid? Viscosity doesn't have a direction.
well, okay, yeah. So this frame dragging thing, right? This example that we worked out, I'm not sure if we can.
The shear thing that comes off diagonal, right? That is the one we are using.
The off diagonal pieces, the VI Vj here. That is shear. Are these the viscosity terms? I don't think so. This is just regular flow. I mean, this is still an ideal fluid with without viscosity.
This V is the like net motion of the fluid, or
Net motion of a fluid element.
so this is the form of the viscous and tensor for ideal fluid
When it's moving, different parts are moving with different speeds. Yeah, it's still an ideal fluid, no viscosity or shear.
I think the definition of ideal fluid was that it has a diagonal
In the rest frame, in its rest frame,
in rest.
in its rest frame. If you're not in the rest frame, then it doesn't have to be true, right? And you can only be, I mean, the assumption we made was all parts of the fluid are at rest with respect to each other. That doesn't have to be true. Okay. But that doesn't tell you that there's viscosity, right? That's still an ideal fluid. Yeah, good questions. Okay, so now let's discuss the next prediction, which is gravitational waves. Okay, so let's consider the linearized Einstein's equations in a region of space-time where there are no sources. Okay, so in the absence of sources, the equation is just this: it's box h bar mu nu is 0. Okay, and what you see is this is just a wave equation. Okay, so it must have wave-like solutions. Okay. Um, so for example, you should have something like e to the I omega t minus z for each component of h bar mu. Okay, this you would expect some kind of solution like this. This is a wave moving along the z direction, and you would expect that this satisfies this equation. Okay. Um, now this h bar mu nu has 16 components. Okay, but so you're solving 16 different equations. Okay, when you're solving this, but it is a symmetric matrix. Okay, h bar mu nu is symmetric because we assume that the metric is symmetric. So there are only 10 independent components. Okay, so if you have a 4x4 matrix which is symmetric, the diagonal and above the diagonal entries are independent. Okay, so that's 4, 3, 2, 1. That's 10 components. Okay, so the metric has 10 independent components. So we have used the gauge freedom to set this condition, okay, partial mu h bar mu nu. But as we discussed in an earlier class, okay, this leaves us with a residual gauge freedom. So we're going to exploit that residual gauge freedom to get rid of some of these degrees of freedom. Okay. Um, in order to make this satisfy this gauge condition, we had made a transformation of coordinates, okay, to x mu plus z mu, which is a function of x, okay, and it results in a change of the metric to first order, which looks like this. Okay, so h mu nu transforms to some h prime mu nu. This h prime mu nu satisfies this condition really, where this is h mu nu plus partial mu z nu plus partial mu xi nu. Okay, and we argued that basically what we've done is if you solve this equation, then the new h prime that you get, okay, will satisfy this condition. Now, it still leaves us with a residual gauge freedom in that we can still make such a transformation. And now if we choose our xi such that box xi is 0, then this condition is still satisfied and therefore the original gauge condition does not change. Okay, so basically we made one transformation like this, okay, with 2h prime mu nu, okay, and we use this xi must have satisfied this criteria, okay, for the original h, okay, so the original h did not satisfy the criteria that this was 0. But if we make this correction to h, okay, by the gauge transformation, where xi satisfies this equation, okay, then the new h prime satisfies this equation, okay, this gauge condition. Now we want to go further, okay, among the h primes that satisfy this condition, okay, you can still make coordinate transformations, okay, and those coordinate transformations are the ones for which box xi is 0. Okay, so there are many such transformations that you can keep making, and now if box xi is 0, okay, this is a further transformation, so you should think of it as a z prime. So now you transform to some h mu nu double prime from h mu nu prime, okay, with some xi prime that satisfies this equation. Okay, and you can use this freedom to reduce the number of components of h mu nu. So I won't work through the details of the math, okay, roughly because it's a little bit boring, but also because it's not particularly illuminating. Okay, so roughly speaking, you have 4 functions, okay, which are xi mu's, and you have to choose these xi mu's to satisfy these equations. Okay, and you can choose it to eliminate some of those 10 components of the metric, this h mu nu. Okay, you can choose those xi mu's to eliminate some of those components. That is, you can choose a gauge in which some of those are 0. Okay, so we'll choose them such that roughly speaking, you can satisfy 4 conditions. That is, you can satisfy h0i is 0, and you can satisfy trace of h is 0, where trace of h is eta mu nu h mu nu. Okay, in the way in which we've been describing this would really be h double prime. After making all the gauge transformations, then this is what's happening. Okay, so from now on, I'm not going to put the double primes. Okay, this is just after we make the gauge transformations. These are the components of the metric that we can set to 0. Okay, so the proof is in section 4.4b of Wald's book. Okay, it's very similar to electromagnetism. Okay, again, in that electromagnetism also, you're trying to solve this equation. Let's say source-free wave equation is this. Okay, and you have this Lorentz gauge condition. Okay, and you can further make a gauge transformation such that a mu goes to a mu plus partial mu alpha. Okay, such that box alpha is 0. Okay, you can further make these transformations, and you can choose, for example, these conditions such that a0 is 0. Okay, this is called the Coulomb gauge. Okay, where you just set a0 to 0 in some particular gauge choice. Okay, so this transformation can always be done in a region where you do not have sources. Okay, that's an important point. This is valid in a region where you do not have sources. Okay, you can be a little more precise about this definition. If you're talking about a point P, okay, this point P should have no sources in its past light cone. Okay, if that is true, then you can always make such a gauge transformation. Okay, I'm not proving the statement. Again, you can see this in Wald. Okay. All right, so now this h is this, and h bar, if you recall, was equal to minus h. Okay, so with our choice with this gauge choice that h is 0, h mu nu and h bar mu nu are the same thing. Okay, there's no difference between them because if you recall the definition, h mu nu is h bar mu nu is h mu nu minus half h eta mu nu. We're setting h to 0 by our gauge choice, so h bar mu nu is just the same as h mu nu. Okay. So it turns out that even though we only insisted on 4 conditions and we had 4 sort of functions to choose, okay, these xi's, to ensure these conditions are true, it turns out that you can also ensure a fifth component of h is 0 for free. Okay, that is, you can also ensure that h00 is free, is 0. Okay, so here we've only insisted that h0i is 0 and h is 0. These are 4 conditions, but it turns out that you can get this fifth condition for free. Okay, also by a gauge transformation. Okay, again, it's not obvious, but you can see the proof involved. Okay, so now finally, if we write down what we're solving box h mu nu is 0, where we're satisfying this Lorentz gauge condition, that is partial mu h mu nu is 0, and we have the conditions are h h is 0, that is the trace of h is 0, and we also have h 0 mu. Whether if mu is 0, that this is the free condition that you got. If mu is equal to I, those are the conditions that we imposed. Okay, so we have basically all these conditions. Okay, and we're trying to solve this. Okay, for h mu nu. So let's count the number of conditions. We have 1, 4. Okay, and this is also 4 conditions. Okay, for each value of nu, it's a condition. So we have. Sorry, this is a differential equation, so it's not really a condition as such. Okay.
When we have written our h mu in the previous lectures, it was already a diagonal.
H mu nu was not diagonal. It was diagonal when we solved for sources which are static. Right, we got -1, -2, 5, 1 + 2, 5. Right. Right now, we're not specifying anything about sources. We're solving source-free equations, the general source-free equations. Right? Okay, so now this general solution to this first equation, box h mu nu is 0, for each component mu nu, okay, you'll have a solution which is a wave equation. Okay, so this wave can be written as h mu nu is a mu nu. These are just coefficients. Okay, for each value of mu nu, I have a different coefficient. E to the I k alpha x alpha. Okay, so this is the general form of the solution. Okay, where k alpha is 0. Okay, that is, if I differentiate this, if I apply box, then what I will get is, I'll get, roughly speaking, I'll get k alpha, okay, times h mu nu. So differentiating this will pull down k alpha is equal to 0, and therefore k alpha must be 0. Okay, so that means if I take k alpha to be a wave vector, okay, of the form omega, where omega is the frequency, k is the wave number. So this is a wave propagating in the z direction. Then h mu nu is of the form a mu nu e to the -I omega t plus ik dot x. Okay, this is a wave equation. Okay, but this omega k satisfy this dispersion relation. Okay, so this dispersion relation tells us that omega square minus k square is equal to 0, or omega is equal to mod k. Okay, this is the same dispersion relation that's satisfied for photons. Okay? Photons moving in the vacuum. So, and this a mu nu must be, now it must satisfy some conditions. This must be symmetric. It must be traceless. Okay, and we've also demanded a bunch of other conditions. That is, since h0 mu is 0, a0 mu is 0 also. Okay, so it's symmetric, it's traceless, and a0 mu is 0. And omega square is equal to k square. So this is a wave-like solution. Okay, and finally now we look at what constraint the gauge condition imposes, this partial mu h mu nu. So that gauge condition will tell us that when I differentiate this with respect to partial mu, that will pull down a k mu. So k mu h mu nu is 0, or k mu a mu nu is 0. Okay, so if our k mu is of this form, it's omega 0 0 omega. Okay, I've just written k, I've just replaced it by omega because it must satisfy the dispersion relation. Okay, so if I write it in this form, then it tells me that I have omega times a0 nu minus a3 nu. So k0 is omega, k3 is minus omega, k with a lower 3 is minus omega. That's why I get a0 nu minus a3 nu. Okay, and now a0 nu is 0 by our gauge choice. Okay, we've already ensured that a0 nu, remember, is the components of this matrix. Okay, so by our gauge choice, h0 nu is 0, a0 nu is 0. That means that this equation, that is that gauge condition that we had, this differential gauge condition, partial mu h mu nu is 0, this differential gauge condition is telling us that A3 nu is 0. Okay, so this gives us some conditions. Okay, so let's look at what the conditions are. Okay, so the conditions are that A0 mu is 0. Okay, or H0 mu is 0. That is, H must have 0 entries for the first column and the first row and the first column. Okay, then we demanded that H is traceless. Okay, but if the trace is evaluated only over this lower 3 block, okay, it's only that these three, the sum of these 3 entries has to be 0. Okay, that's the traceless condition. Then this other condition, by the Lorentz gauge condition, tells us A3 nu is 0. That tells us that any third row or third column of this matrix is 0. That is, this row is 0 and this column is 0 and this row is 0. Okay, this last row, this last column. So the tracelessness condition now tells us that if this entry is H plus, this entry must also be minus H plus. Okay, so that it's traceless. And now this is a symmetric matrix. So if I choose this other entry to be H cross, this other entry also has to be H cross. Okay, so there are only 2 free numbers that you can choose to define this A mu nu. Okay, either H plus or H cross. Okay, and this is multiplied by e to the minus I omega t minus z. Okay, for a wave propagating in the z direction. So of course, if it's in the x direction or y direction, then you have to change things. So you see that the non-zero entries are only the xx, xy, yx, and xx entries. This is true for a wave propagating in the z direction. Okay, if the wave is propagating along the x direction, then appropriately you have to change which components of the matrix are non-zero. Okay, so this is for a wave propagating in the z direction. And we see that there are only 2 independent components of this matrix, which are H plus and H cross. Okay, why have we written them as H plus and H cross? We'll see why in a moment. Okay, so this is very similar to the 2 polarizations that you get for an electromagnetic wave. When you solve the wave equation for photons, okay, you're solving these equations. Box A mu is 0, partial mu A mu is 0. Okay, and you get A mu is, let's say you can write them, the solutions as in the gauge where A0 is 0. Okay, this is the Coulomb gauge. Okay, and you've also imposed this condition. Partial mu A mu is 0. Okay, you've imposed this condition. Okay, when you impose this condition, the solutions that you get are of this form. It's AX 0100 e to the minus I omega t minus z. Okay, this is one solution. And the other solution is 0010 e to the I omega t minus z. This condition will tell you that A3 is 0. Okay, for a wave moving along the z direction. And this is the extra condition that you imposed. Okay, so now with these extra impositions, okay, this is basically what you call a wave which is polarized along the x direction. This is a wave which is polarized along the y direction. In electromagnetism, this is how you define polarization. And you can also take linear combinations of these polarizations to get circularly polarized light. Okay. 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 Just as an interlude for the moment. So what we've seen is that the general perturbation, okay, that we can write down to the metric is you have the scalar perturbation. Okay, this is for static sources. Then you have this AI, which is what is called a vector perturbation. This you can have in this you can have when the sources are moving, you consider the velocities. And then you have this Hij, okay, which is a tensor perturbation. This can be sourced by something, okay, but we're solving the equation in a region where there are no sources, okay. So it can also be sourced by something. Okay, so this is the most general form of the perturbations to the metric tensor. Okay, okay. Right now we're only considering this part. Okay, that is the tensor perturbations. Okay, so the question is now. So now that you can have these gravitational wave solutions, okay, it's a separate question. What produces these gravitational waves? Let's ask the question: what happens if a gravitational wave passes through you, okay, or passes through some test objects? So what is the effect of a gravitational wave passing through some test particles? Okay, so our G mu nu was eta mu nu plus H mu nu. This is the metric. Okay. Now, obviously, our H mu nu now obeys this wave type solution. So that means that the metric, the space-time distance between space-time points, is going to oscillate as a function of time. Okay. So if you have a single test particle in free fall, there's no physical measurable effect, okay, that you can see. Okay, you have to compare two different particles, and you have to see what the effect is on these two different particles. Okay, because a single particle will follow a geodesic. Okay, and if it follows a geodesic, it's like an inertial object, right? There's no test that you can do to really tell the difference. So even, for example, when you have curvature for the metric, we've seen you have to look at nearby objects. When you have nearby objects, those nearby objects will experience the deviation between their geodesics, right? That will change as a function of time. They'll experience relative acceleration. Okay, so that is kind of the effect that we're going to look for. So we'll consider a collection of test particles, and these test particles will experience tidal forces. Okay, that is, if you imagine a test particle which is following a geodesic, this is a path through space-time, and another test particle following a geodesic. If you recall the geodesic deviation, t is the tangent vector along the geodesic, but x is the deviation vector. That is, as I move from one geodesic to another, or as I move from one test particle to another test particle. Okay, so we have derived this important geodesic deviation equation, which is what is the law that this deviation vector satisfies. Okay, this x, and we had found that we had shown that d square x mu d tau square is related to the Riemann tensor r mu nu rho sigma t nu t rho x sigma. Okay, so the idea will be that when you have the flat metric, of course, there's no curvature, there's no geodesic deviation. Okay, but once you have this h mu nu, in general, you will introduce curvature. Okay, if you introduce curvature, then that curvature will lead to geodesic deviation, and that is a physically measurable effect. Okay, what is the actual effect? We'll see in a moment. Okay, so what did you actually measure? We'll see. So let's consider two test particles which are at rest. Okay, so imagine that you have two test particles sitting here which are at rest. So t nu is just of the form 1, 0, 0, 0. So t nu is just the tangent vector, which is dx nu d tau. Okay, and this is slowly moving. Okay, and since it's slowly moving, again you can dx d tau, if this is 1, what it tells you is dx0 d tau is 1, or x0, you can choose it to be tau, and x0 is nothing but time. Okay, so the time that passes for each of these particles is just approximately an affine parameter. Okay, it's this tau. Okay, so what we want to do is now solve this geodesic deviation equation. Okay, and the only non-zero components of t nu and t rho are when nu is 0 and rho is 0. Okay, because we've taken t nu to be 1, 0, 0, 0. Okay, that is, it's slowly moving. This is just the forward velocity of the particle. Okay, so you have two particles which are at rest. Okay, this is the geodesic deviation equation that you need to solve. So we just need to work out what are the components of the Riemann tensor given our metric perturbation. Okay, given the metric perturbation h mu nu. So we plug in our into our formula. Okay, this Riemann tensor is already first order. Okay, so we don't need to look at x to first order. Okay, so Riemann tensor is already going to depend on h, or derivatives of h. H is a first order perturbation. So okay, so I'll let you work it out, but I just plugged it into that formula that we had. Okay, for the Riemann tensor in terms of second derivatives of the metric. Okay, and the metric, of course, the eta mu nu part doesn't contribute, so it's all derivatives of h mu nu. Okay, and you get something like this. Okay, plus there are other terms which are quadratic in gamma. Okay, which are quadratic in h, which I've dropped. Okay, now if you look at this, for a general perturbation, we've taken h0, 0 is 0. We've chosen that gauge where h0, 0 is 0. So this is 0. And we've also chosen h mu to be 0. So this is 0, this is 0. Okay. So the Riemann curvature tensor is quite simple with our gauge choices. Okay. It's just half partial 0 square h mu sigma. Okay. So our geodesic deviation equation now is partial square x mu partial t square is equal to half x sigma partial 0 square h mu sigma. Okay. Okay, so it's relatively simple. Okay, it's so now we want to solve this equation. So given a gravitational wave, so if you tell me what h mu sigma is, let's plug in our wave solution. Okay, let's ask what happens to the deviation vector between two particles. Okay, that is these two particles. Okay, the separation. What is going to happen to that vector? Okay, as the gravitational wave passes through them. Okay, so again, we'll consider a gravitational wave in the z direction with frequency omega. Okay, that's the one for which we had written this explicit matrix. Okay, so only H11, H12, H21, H22 are non-zero, right? Those are the components which are non-zero. And so only the deviation vector components in the xy direction are important, okay? Because if you look at this, okay, if I take mu to be 0 or mu to be 3, right, then this mu is 0 or 3, and h0 3 or h0 anything is 0, h3 anything is 0. Okay, so I only care about the deviation between these two particles in the yz direction, sorry, in the xy direction. Okay, so the idea is that I have two particles, a gravitational wave is passing through, the wave is moving along the z direction. Okay, so let's say it's coming out of the paper. I'm looking in the xy plane. Okay, and if I have two particles here, I want to know what happens to the deviation between those two particles. Okay, that's what we're trying to find out. Okay, and the deviation will only be in the xy plane. It will not be in the z direction, and it will not be in time. Okay, the deviation vector is only going to be in the xy direction. Okay, xy directions. So now what we do is we take this equation. Okay, so we'll just work out. So we'll assume that this capital X only depends on time, right? Okay, so so we'll fix the separation and only look at the time dependence of this. Okay, so we'll write d square x1 dt square. So I'm just writing the components of this for mu is equal to 1 and 2. So we'll have d square x1 dt square is equal to, now when I take the second time derivative of that plane wave solution, I will pull out a minus omega square. Okay, when I differentiate e to the I omega t minus z. Okay, if I differentiate this twice with respect to t, I'll pull out a minus omega square. Okay, and I'll still have this e to the minus I omega t minus z. And the other thing that you can sort of see is you'll have x1, sorry, I'll have partial 0 square h1. Okay, and the only non-zero components are h1, h11 and h12. Okay, so I'll have something like this, x2 partial 0 square h12. H11 was h plus, h12 was h cross. Okay, so I'll have something like x1 times h plus x2 times h cross. Okay, times this e to the minus I omega tz. Okay, so this is the first equation. And the second equation will be very similar, d square x2 dt square is equal to minus omega square x1 h cross minus x2 h plus, okay, e to the minus I omega tz. Okay, yeah, and this minus sign just comes from the fact that this is the 1 1 component and this is the 2 2 component, and the matrix was traceless. That's why there's a minus sign here. Okay, this was minus h plus was the entry. Okay, so this is great, right? Now what we need to do is we have two particles. Okay, so let's understand what we're solving. Okay, so we have two particles. This in the xy plane. They are separated by an amount x1 in the x direction. Okay, and they're separated by an amount x2 in the y direction. So these two particles are here. Okay, and a gravitational wave is now passing through and it's coming out of the paper. Okay, it's coming out of the paper. And what we want to do is we want to find what happens to the separation x1 and x2 as a function of time. Okay, we're solving these equations to figure out what is happening to that separation. Okay, the separation x1 and x2 as a function of time. Okay, so that is the deviation vector is changing as a function of time. So these particles are going to change their relative positions to each other as the gravitational wave passes through. Okay, what we want to do is we want to solve for x1 and x2 as a function of time. Okay, now you can look at these equations, and so let's solve them with, let's say, only h plus is non-zero or only h cross is non-zero. Okay, it's simpler to solve it that way. So let's solve, because basically what we're doing is solving for different polarizations of the gravitational wave. Okay, so we'll take h plus to be non-zero. So in the case where h cross is 0, these entries are d square x1 dt square is minus omega square x1 times h plus e to the minus I omega t minus z. Okay, so I've written this as a matrix equation. So d square x1 dt square and d square x2 dt square, I've written both the equations together. is equal to minus h plus omega square. And now I have this diagonal matrix 1, 0, 0, minus 1. Okay, times x1, x2 e to the minus I omega t minus z. These are the equations that I've solved. Okay, h plus, remember, is a small number. Okay, because I'm assuming that this is this gravitational wave is a perturbation. Okay, it's a tiny perturbation. So now let's work out the solution. Now if you didn't have this factor, the solution would be quite simple, because this is just a second order, ordinary second order differential equation. Because you have this explicit factor, okay, you can't solve this exactly, right? Because there's an explicit time dependence on this side. However, you can solve it perturbatively again. Okay, you can solve it perturbatively, realizing the fact that h plus is small. Okay, since h plus is small, you can solve this perturbatively. And the solution is such. Okay, so if we set h plus to 0, okay, and we assume both the particles are at rest initially, then x1 is some constant, which we'll call a, and x2 is some constant, which we'll call a. Okay, or sorry, let's call them a1 and a2. Okay, so this is the solution in the absence of the perturbation. Now we want the correction to this. Okay, in the presence of a perturbation. So in the presence of a perturbation, you can still solve this equation quite easily. Okay, I'll just write down the solution and you can check. Okay, by plugging it in, that this is what you would get. Okay, so the solution is this: a1 is a constant times 1 minus half e to the minus I omega t minus z h plus. Okay, and a2 times 1 plus half e to the minus I omega t minus z h plus. Okay, these are the solutions. Okay, so so what we can do is we can write the second solution. Okay, as again we can absorb this. So this is the difference is there's a plus sign here and there's a minus sign here. What you can do is you can absorb this plus sign into a phase over here. Okay, so you can write this as x1 is equal to a1 minus h plus by 2 e to the minus I omega t minus z, and x2 is 1 minus h plus by 2 e to the minus I omega t minus z plus pi. Okay, where I've just absorbed I've made this plus sign into a minus sign and absorbed this here as an e to the I pi. Okay, so now let's try to understand what's going on. Okay, so if we have a ring of particles, right, so the separation in the xy plane of any two of these particles, okay, the separation of any two particles, so there's a delta x1, delta x2, okay, which is the separation between them. In the separation is in the x direction, one separation is in the y direction. Now what we're saying is, to leading order, that separation is constant. Okay, these particles are static. The correction to this, okay, is that there is oscillation. Okay, that this delta x1 changes, okay, by this amount. Okay, it changes by this amount. The amplitude of that oscillation is a times h plus. Okay, the amplitude of that oscillation. So this delta x1 is fixed. It's roughly a, but it's oscillating. So there's a correction to this, which is an oscillatory term. So we'll take the real part of this, obviously, because we want real solutions. So times some cosine of omega t minus z. Okay, so this is the correction. So the distance between them in the x direction is oscillating. Okay, it's oscillating with this small amplitude a times delta h1. Okay, in the y direction, it's also an oscillation. Okay, but the oscillation is out of phase. Okay, it's a delta h or a2 delta h. Delta h is the same. Okay, times cosine omega t minus z plus pi. Okay, so it's exactly 180 degrees out of phase in the oscillation in the x direction. So which means these two have fixed separation. In the x direction, let's say they separate further from each other. But when they separate far from each other in the x direction, in the y direction, they're at their closest approach. Okay, and vice versa. When they're at the farthest in the y direction, they're closest in the x direction. Okay, so so now if you want to visualize this, maybe I can show you a sort of movie of this. Okay, I just show you in Sean Carroll's book. Okay, it's just easier to see. Oops. Okay. Yeah, okay. So this is what happens, okay, for the H plus polarization, if I start with a ring of particles, okay, which is the leftmost circle, okay, now what is going to happen is that this circle will, let's say, squish in the X direction and expand in the Y direction, okay. So that is, the particles will sort of come together along the X direction, but spread out in the Y direction, okay. Then they will again come back, okay, to their original position. Then they will spread out in the X direction, but now squish in the Y direction. Okay, that's the fourth figure over here. Okay, then again they'll come back. Then again they expand in the Y direction and squish in the X direction. Okay, so this is what happens when the gravitational wave passes through. They're all maintaining their relative positions. They're oscillating about their relative positions. Okay, they're just squishing in the X direction when they're expanding in the Y direction. Okay, or they're sort of squishing in the Y direction when they expand about the X direction. Okay, so this configuration is called a plus type oscillation. Okay, because this circle, okay, kind of squishes to an ellipse like this and then an ellipse like this. So it traces out a plus. Okay, so this is called, that's why it's called H plus. Okay, this particular polarization. Now, similarly, you could work out what happens for H cross. Okay, I'll leave it as a homework exercise to do this. Okay, but you can, I've written it in the notes. Okay, so you can look it up. But really what happens is that with the cross polarization, you still have a plus, but the plus is at a tilted direction. It's in the x1 plus x2 direction and the x1 minus x2 direction. Okay, so with the cross polarization, in the x1 or the x plus y direction or the x minus y direction, in the x plus y direction you squish, in the x minus y direction you extend. Okay, and vice versa. In the x minus y direction I squish, in the x plus y direction I extend. Okay, so so that's what's happening here. Okay, so these x plus y and x minus y directions are 45 degrees to the x and y axis. So here I will squish in one direction. Okay, so I squished in, let's say this is the direction of x plus y equal to constant. Okay. Anyway, it doesn't matter. One is x plus y is constant, one is x minus y is constant. Okay, so you see that now it squishes, sort of it expands this way or it expands this way. Okay, and that traces out a cross. Okay, so that's why this other polarization is called H cross. Okay, so depending on which type of polarization you have, okay, the matter particles will either squish in this plus configuration or they'll squish in this cross configuration like that. Okay. Now you can also take superpositions of the H plus and H cross, just like you took for linearly polarized light. You take superpositions which are which give you circularly polarized light. In this case, you can take a polarization like H plus plus IH cross. Okay, that's what's written here, which is called right circularly polarized, and H plus minus IH cross. Okay, and what will happen in this case is is that first of all you'll distort this circle into an ellipse, and then this ellipse will just rotate. Okay, the ellipse will just rotate with some particular precession. Okay, so if you didn't have a gravitational wave, these particles would be along a circle, but with circular polarization, they would all basically first get squished into an ellipse, and then the ellipse itself would rotate. Okay, so this is sort of the picture of what happens in these circular polarizations. Okay. Okay, I won't walk through all these details. Again, I worked it out for one polarization. You can try to work it out for the others. Okay. Okay, so in electromagnetism, you might be familiar with the fact that a photon is what is called a spin 1 particle, and it's also a massless spin 1 particle. A massless spin 1 particle has two polarizations. Okay, these are the two linear polarizations. Similarly, a massive spin 2 particle, okay, which is these gravitational waves, okay, they have two polarizations also. Okay. Okay, so now let me just very briefly now just tell you about a few other things. Okay, now we've seen what the effect of gravitational waves is on test object, but let's ask what can produce these gravitational waves to begin with. Okay, so this discussion, I'm not going to go through the derivation because it's rather long. Okay, so I'll just tell you the result. Okay, which you can look up the derivation if you like in section 7.5 in Carroll. So what you can show is that if you have, okay, you can of course work it out exactly, maybe numerically. Okay, but in some certain approximations, you can work out exactly a very simple form for the production of gravitational waves and you can estimate what the typical amplitudes this h plus and h cross are for certain sources. Okay, so if you can show that if you have a weak source with size L, such that the wavelength of photons is much smaller, okay, than the size of the source. Okay, so it's a big source compared to the wavelength of the gravitational waves that you're emitting. And if you're at large observational distances, so I have a source which is spread out, but I'm very far away from this source. Okay, then the gravitational wave amplitude, that is the h bar ij, okay, or in the gauge that we're using, h bar ij is the same as hij, okay, is 2g over c to the 4 times r. Okay, I'll drop the factor of c because I'm using c as 1. Okay, d square iij dt square. Okay, but this derivative with respect to time is evaluated at something called retarded time, which is tr is equal to t minus x by c. So I'm evaluating the gravitational wave amplitude at some t and x. Okay, I'll tell you what this is in a minute. Okay, so let's just look at it pictorially. So this is us. This is a large distance r between us and some source. Okay, this is a source that is spread out over some length L. Okay, this length L, the typical size of this source, is much greater than the wavelength of the gravitational waves that we're looking at. Okay, in this approximation, you can work out that the amplitude of the gravitational waves hij tx that you measure at your position, okay, will depend inversely on the distance between you and this source, okay, as 1 by r. Okay, that's not surprising because then the amplitude square will fall off as 1 by r square. Okay, if it's emitting in all directions. Okay, we're assuming the source is isotropic. Okay, times d square ij. Sorry, we're not assuming it's isotropic. I should take that back. Okay, d square iij by dt square, where iij is the moment of inertia of this source. Okay, it's just your standard moment of inertia, which is rho x xi xj. Okay. Sorry, this is the quadrupole moment, okay, of the source. This is what we call the quadrupole moment. It's the density weighted by xi xj. Yeah, it's also what we call the moment of inertia, okay, of this object. Okay, so this is integrated over the entire source region. Okay, now the thing is, why would this change as a function of time? Well, if the source is not static, okay, as a function of time, let's suppose its quadrupole moment changes, then so imagine that the source is, let's say, pulsating for some reason. It's being driven to pulsate, or you have two masses which are rotating around each other. This would also cause a quadrupole moment, which changes with time. So so a changing quadrupole moment, the second derivative of the changing quadrupole moment would control hij. But the other thing that you learn from this is that this changing quadrupole moment is occurring at an earlier time, which we call tr. Okay, which is t minus r by c, okay, where r is this distance. So it takes time. So if there's a disturbance here occurring at tr, okay, a time r by c later, which is the time it takes for this wave to travel from there to us, a time r by c later, tr plus r by c is t. Okay, at time t we will experience that effect. Okay, so so there's a delayed effect, right, because this gravitational wave will also propagate at the speed c. Okay, it'll propagate at the speed of light. Okay, and that's also what you expect from the wave equation. From the wave equation, it satisfies. It's the same wave equation with the same constant c for gravitational waves as it is for electromagnetic waves. So gravitational waves will propagate with the same speed c as electromagnetic waves. Okay, in this linear approximation. Okay, so the difference between these gravitational waves and electromagnetic waves is, unlike electromagnetic waves can be sourced by dipole radiation. Why is dipole radiation possible? Because you can separate out positive and negative charges. For gravitational waves, you can't separate out. There's only one type of charge. Okay, they're all positive charges. So you can't create dipole radiation. You can only create quadrupole radiation. Okay, so the gravitational waves are sourced by quadrupole moments because there are no negative masses. Okay. Okay, and roughly speaking, you can work out what this amplitude is now. We'll just do an order of magnitude estimate. Okay, so we'll just look at these factors. H is 2g by r. Moment of inertia is roughly m times r square, where r is the size of the source. Okay, and if we're taking second derivative, then it's roughly some omega square, where omega is some frequency with which the source is oscillating. Okay, So this is roughly an estimate of what h is. Okay, and I can stick in factors of c to make it dimensionally correct. H has to be dimensionless. Okay. Okay, so I have to. This is you have to stick factors of c back in here, but you can quite easily do this. Okay, and now this gm by c square is again the Schwarzschild radius, okay, of the source. So it's like some Schwarzschild radius of the source times r square, which is the actual size of the source, divided by the distance to the source times some characteristic oscillation frequency of the source. Okay, this is roughly speaking the this amplitude of the gravitational wave. So what you can do is you can plug in typical values of the mass of the source. Okay, so imagine that you have two binary stars with a mass of 1 solar mass, and these binary stars are orbiting each other with the same distance that the Earth is from the Sun, which is 1 AU, which is about 150 million kilometers. Okay, and you can take the orbital frequency using standard Keplerian motion. Okay, and you can work out what the orbital frequency is. It's roughly, you can express it in terms of the Schwarzschild radius and the distance between the two objects which are orbiting around each other, okay, which are at distance r. And so we'll write this as c rs to the half over r to the 3/2. This is the orbital frequency. And we know that for any object going around the sun at the distance from the Earth, its oscillation period is roughly of the order of a year. Okay, why roughly a year? Because the Earth is massless. Okay, if the Earth had the same mass as the sun, then you should use the reduced mass of both of them to determine the orbital frequency. Okay, so anyway, we're just doing an order of magnitude estimate. So let's just say 1 year. The distance, let's assume that this is a distant galaxy at a distance of what is called 10 megaparsecs. 1 megaparsec is 2 megaparsec is the distance to the Andromeda galaxy, roughly speaking. 10 megaparsecs is still roughly our local neighborhood of galaxies. Okay, more likely we'll see things from further away, like hundreds of megaparsec, where 1 megaparsec is about 3 light years. Okay, so I'll write this as 30 into 10 to the 6 light years. A megaparsec is a million light years. Okay, a megaparsec is a million parsecs. 1 parsec is 3 light years. Okay, roughly. So if you plug in the numbers and you do the estimate, okay, for all of this, what you would get is the amplitude is 10 to the minus 30. Okay. Now, obviously, if the objects are more compact, okay, that is, the objects are closer together, r will be smaller, okay, but the orbital frequency will be larger. Okay, the orbital frequency gets larger as r gets smaller. So the orbital frequency gets larger, and therefore the total amplitude will actually get larger. Okay, if they're very compact and they're orbiting very close to each other. Okay, so if they're orbiting within, let's say, a few Schwarzschild radii, for an object of the mass of the sun to be orbiting within a few Schwarzschild radii of something else, you already have to compress the sun to a very small size. So it's almost like you're talking about a black hole or a neutron star already. Okay, so we'll imagine such objects, okay, which are very compact, and we're looking at an object which is maybe 10 times. They're orbiting at a distance about 10 times the Schwarzschild radius. So the Schwarzschild radius for a solar mass object is about 3 kilometers. Again, if you plug in the numbers, okay, you'll find that the orbital frequency is about 100 hertz. Okay, so it roughly takes 0.01 seconds, okay, to go around. Okay, so one black hole going around the other black hole at a distance of about 30 kilometers, okay, is roughly going to take about 0.01 seconds. So very quick, okay, that orbit, and right, because you're talking about 100 kilometers and you're covering it in at a time of 0.01 seconds. Okay, so it's very quick. Okay, and nearly traveling at the speed of light. Okay, and let's imagine now that this is very far away. It's 100 megaparsecs away. Then what you'd find is h is of the order of 10 to the minus 21. Okay, so you'd find that basically regular binary stars, which are far from each other at typical distances at which you find stars, those stars will give you a much smaller amplitude, maybe 10 orders of magnitude, 9 orders of magnitude weaker. Then if you had black holes which are very compact, very close together, which are orbiting each other with a tight orbital frequency, okay, in that case you would find an amplitude which is 9 orders of magnitude larger. So black holes or neutron stars orbiting just before they coalesce will emit these kind of gravitational waves, which you can detect. Okay, and the frequency will be of the same order as the orbital frequency. Okay, it will be of the order of this 100 hertz. Okay, however, this effect is still very, very, very weak. Okay, because h is still 10 to the minus 21. So what does that h mean? Okay, so we discussed if you have two particles which are separated from each other. Let's imagine that you even separate them by a distance of 1 kilometer. Okay, so I hold them very, very far apart. Okay, but now the change in the separation, by the separation, that is the amplitude by which they'll oscillate as the gravitational wave passes through. This is of the order of h. Okay, so if two particles are at a distance L, they will oscillate about their mean position with an amplitude delta L. Okay, so they will go to L plus delta L and L minus delta L, and the delta L is h times L, right? Because we saw that the amplitude or the change in position is a plus h times a, okay, times some cosine. Okay, that's roughly what we have. So now imagine that you have particles which are 1 kilometer apart. Okay, then the amplitude of oscillations delta L is 1 kilometer times this 10 to the minus 21. And what you get is 10 to the minus 18 meters. Okay, so that's a very, very, very tiny change in the distance between these two objects. So if you compare this, you're talking about the size of an atom is only 10 to the minus 10 meters. Okay, the size of the nucleus of an atom is 10 to the minus 15 meters. This is an impossibly small distance, right? So even though a gravitational wave might be passing through you, how will you detect it? The components of your detector are bigger than the size of the deflection that you have. Okay, and you have to measure the precision down to the size of a single atom. Okay, it sounds impossible to do this. Okay, so how can you ever hope to detect such a tiny effect? Okay, remarkably, such a detection was made in 2015. Okay, and this was the remarkable discovery by LIGO. Okay, so LIGO is a laser interferometer. So you shoot a laser like this. Okay, and it's a beam. You have a beam splitter here. This is very similar to the setup of the Michelson-Morley experiment. It's just an interferometer. So you have two arms. Okay, so light goes one way into one arm, and light goes into the other arm. And this arm has a length L, and this length L is let's say 4 kilometers. Okay, this is the length of one detector arm. Okay, and inside, instead of light coming back, okay, it actually bounces around many times. Okay, and similarly here it bounces around many times, and then it's allowed to come through. Okay, so the effective path length is increased by the fact that you allow it to bounce around many times. Okay, and then what you do is you look at these two light beams, you measure them on a detector. Okay, so you measure the interference between these two. Now, if you tune the path lengths, okay, to be exactly the same, then you will have constructive interference here. Okay, if you tune the path lengths to be slightly different, then you might get destructive interference. So you choose them so you get maximally destructive interference. Okay, so that is you get a dark spot. Okay, so you tune them so that you get a dark spot over here. Now, this is when there's no gravitational wave passing through. When a gravitational wave passes through, it will change the lengths of these interferometer arms. Okay, and it will change one length differently from the way it changes the other length. Okay, depending on the polarization of the gravitational wave. Okay, so what that will do is it will cause a change in the interference pattern. So instead of a dark spot now, you'll see some photons. Okay, so you'll see some photons actually clicking on your detector. Okay, so if you can measure these photons that are clicking in your detector, then you are basically going to measure the gravitational wave, and you will see the number of photons, the clicks of those photons change as a function of time. Okay, that will tell you basically the oscillation pattern of the gravitational wave. Okay, so now you've increased your effective path length. Okay, so this L prime, so you make the light bounce around about 200 times. Okay, instead of just once. So that gives you a path length which is larger by a factor of 200. Okay, so it's 200 times 4 kilometers. So the effective path length is larger now. It's 800 kilometers. Okay, and the accumulated phase shift that you pick up, okay, this extra phase that you pick up will be the extra path length times 2 pi by lambda. Okay, that's the extra phase difference between these two light beams, this one and this one. Okay, where delta L is the change in length of one arm when a gravitational wave passes through. Okay, when a gravitational wave passes through, then you'll get an extra phase shift, which is delta L times this extra factor of 200 because it has to bounce around 200 times. Okay, this is the extra path length that you get. Path length divided by lambda is the extra number of cycles, okay, of the waveform, okay, that you will produce, and times 2 pi is the extra phase. Okay, so this is the extra phase that you get. Okay, so if you had tuned it to destructive interference, you will now pick up this extra phase, okay, of delta phi. Delta L will be roughly h times L prime. Okay, where L prime is the effective path length of 800 kilometers. Okay. Oops. Okay, so you can work out what the phase difference is, okay, for these numbers. Okay, so I just plugged in h is 10 to the minus 21, L prime is 800 kilometers, okay, and lambda, let's assume you're using visible light laser, 500 nanometers. Okay, you can plug in the numbers, and what you get is a phase difference of 10 to the minus 9. Okay, so you have to build an interferometer. Even with all this bouncing around 200 times, you have to be sensitive to a phase difference of 10 to the minus 9. Okay, how can you be sensitive to such a phase difference? This is a rather small phase shift. Okay, and we are assuming that we have a dark spot, and basically what you're saying is that because of this dark spot, now if I change the interference pattern, so initially you imagine that you have two waves of amplitude A1 and A2, and their phase difference is phi. You've tuned the phase difference or the path length such that cosine phi is minus pi, and they destructively interfere with each other. So let's say A1 plus A1 and A2 are the same amplitude. Okay, then what will happen is that they will destructively interfere. Now this phase difference is getting an extra phase because you're changing the effective path length, okay, of one arm as a gravitational wave passes through. And now you want to see what is so IS0 is destructive interference, but now you get some non-zero intensity, okay? And you want to measure this non-zero intensity, okay? And roughly speaking, now in order to measure this intensity, okay, you will always have some amount of noise in your detector. You may do whatever you can to reduce the amount of noise so that those path lengths do not change, but there will still be quantum mechanical noise. Okay, that quantum mechanical noise is called short noise. Okay, which means that even when you have destructive interference, okay, if your wave has some, in the regions of constructive interference, if you have some number of photons n, okay, then you will always have an uncertainty on this number of photons delta n, just due to quantum mechanical effects. Okay, it's really like I'm trying to measure a wave of photons, okay, and I'm trying to measure this wave of photons by discretely counting the number of particles that I have in this wave, okay. So this wave particle duality, okay, and roughly speaking, there's an uncertainty principle of counting photons and trying to measure the wave-like property, which is a phase, okay. This is the so-called uncertainty principle, the number phase uncertainty principle, okay. So if I try to measure the number of photons very accurately, then the phase will be highly uncertain. Okay. And now I'm trying to measure the number of photons down to saying there are exactly 0 photons. When I say exactly 0 photons, yes, but to what error? Okay. Am I saying that there are exactly 0 photons? So if I have a wave with, on average, in the constructive spots, if I see n photons, in the destructive spots, just this short noise will produce square root n photons. Okay. This short noise will produce square root n photons. So what I need to do is have, I need my uncertainty, I need this to be very small, okay? So even if I set this to its minimum uncertainty, so delta n, delta phi is order h cross, I need delta phi to be of the order of, I need to measure the uncertainty to within this, okay, which is h bar by root n. Okay, so if I want to measure the phase very precisely, I have to increase the number of photons that I see. So I have to use a very intense laser. Okay, when I use a very intense laser, then the noise in the counting of the number of photons, the relative noise decreases. Okay, and I can measure the phase to very high precision. Okay, so it's not a it's very technically challenging to have this high precision, high focus laser for which you can measure these tiny phase shifts, okay, of 10 to the minus 9 as a gravitational wave passes through. Okay, so it's very similar to what you've done with, let's say, Young's double slit experiment. I don't know if you've done the labs yet. Okay, Young's double slit experiment or a diffraction experiment where you're measuring a shift in the fringes, right? But imagine that fringe shift is so small that it's not even shifting by one fringe. It's shifting by 10 to the minus 9 fringes. Okay, and you're trying to measure that effect. Okay, that's ridiculous that you can even measure it, right? But they have been able to do it. Okay, by measuring very precisely the locations of the fringes. Okay. Okay, so basically, let me just tell you in the last 2 minutes about these experiments. LIGO, okay, is a laser interferometer which is ground based. Okay, so it has two detectors, and both detectors simultaneously detect these gravitational wave signals. They've seen it from black holes, black hole neutron star mergers, and so on. Okay, and 2015 was this big discovery. We have, in some sense, indirectly detected gravitational waves before, as far back as 1974, where we observed these two pulsars, okay, a pulsar in a binary system. This pulsar was going around another star. We didn't directly detect the gravitational waves, but as this pulsar was going around, what general relativity predicts that it should emit gravitational waves. Okay, these gravitational waves will cause it to lose energy and fall further in, okay, in its orbit. Now, what should happen then is that these pulsars emit radiation in very periodic bursts. Okay, this will alter the time period between those pulsations. Okay, and you will basically detect that altered orbital frequency. So it's sort of an indirect measure of the fact that the orbital frequency of this pulsar has changed, and therefore it must have emitted something. What it emitted was gravitational waves. You assume that that's true, but the rate at which its orbit is decaying is consistent with the predictions of general relativity. Okay, so that was the indirect observation of this Hubble-Stellar pulsar. I think it won a Nobel Prize also. Okay, what is the future going to look like? Well, in the future, we're going to launch satellites into space. Okay, do the same interferometer measurement in space. What are the advantages of being in space? One is you can have a longer path length, okay, because these detectors can be very far from each other. The second advantage is you have less noise. Okay, on the ground, many things can cause vibrations. Those vibrations can alter the path length between these two. You need to minimize those vibrations by having damping to prevent those things from vibrating. But in space, you don't have all those vibrations. Okay, so you eliminate a lot of the noise. So LISA is a future space-based proposal where you'll have three detectors in space which are shooting laser beams towards each other and measuring the path lengths between themselves. Okay, and you can use this to detect gravitational waves passing through. Okay, and this will be sensitive to a completely different range of frequencies where you will detect not just solar mass objects which are merging with each other, but you will detect supermassive black holes, okay, which are believed to be at the centers of galaxies, which have million solar masses. Or you might detect things like stochastic gravitational wave backgrounds if there's a phase transition in the very early universe, very similar to a water ice type transition, but much more with fundamental particles, okay, happening in the very early universe. Those phase transitions are also expected to produce gravitational waves, and you might detect signatures of those, which is called the stochastic gravitational wave background. This will be coming to you from all directions. Okay, so you can't really tell, pinpoint a particular direction on the sky where it's coming from, but you'll see these gravitational waves coming from all directions. So this could be a signature of primordial phase transitions. Okay, so this is very likely around the corner in the next decade or so. Okay, so it's a very exciting field with a lot of future observations and things that were once thought impossible. Right, this kind of measurement of gravitational waves has become a reality. I mean, only in the last decade, right? And in the future, I'm sure there's going to be much more to do. Okay, I think that's it. I'll stop here. If there are any questions, you can ask.
So like the gravitational waves are stretching across spacetime itself, right?
Yeah.
Which means that the wavelength should also change of the light that is being seen.
Of the light which is incident. Yeah, but that's a subdominant effect, right? Because the wavelength of the light is very tiny anyway. So now the wavelength is changing by a fraction, which is 10 to the minus 21.
When we're working with such small numbers, then that also matters.
No, this will be second order in H, this effect that you're talking about, right? Because what we're measuring is already 2 pi by lambda times H, right, times L. And what you're saying is L changes now to lambda changes to lambda plus H lambda. That's going to give you an effect which is second order in H. Yeah, so you can have gravitational waves from a supernova explosion, let's say. Okay, people have, I think, tried to look into what the effect would be from a supernova explosion. I think it would have to be relatively close by for that to happen. See, even for these gravitational waves, you have to have compact objects, right, which are going around, and only when they're very close enough is the amplitude sufficiently large. Um, yeah, in fact, the estimates that we did are not quite right because our estimates are sort of using Newtonian expression for the quadrupole moment and so on. Okay, it's actually going to be a strong source, and so you can't use. But for order of magnitude estimate, it's fine, right? Um, so even a supernova explosion, basically, it's not compact enough that you get these strong quadrupole moments, right? And that's really the main reason why. So if it's nearby, if it's in a galaxy, then maybe you'll get a signal. But if it's far away, then it's very difficult to get a signal. The rate for supernovae is this so-called core collapse supernovae is that you have 2 per century, okay, in any galaxy. That's the rate that we've seen by looking at other galaxies. In our own galaxy, we have not seen one in the recent past, okay, but maybe several hundred years ago we saw one, okay. In our own galaxy, we're sort of overdue, okay, for a supernova, and there's a lot of interesting science you can do if you detect such a core collapse supernova. One of the signatures could be gravitational waves, but you'll also see it in visible light. You'll also detect neutrinos from these supernovae. So that would be really exciting. It's something called multi-messenger astronomy, where you can measure something not just in light and neutrinos like we've done so far, but you could also measure it in gravitational waves. Yeah.
Stretching of the length happens only while the wave is passing through, right?
Yes.
So is it a pulse or is it a function?
It's a pulse. So when they're merging, the amplitude is strong. And then once they merge, so what happens is you have to actually calculate this in a strong gravity regime. So you can't show this. What I argued is only about the in spiral phase. But once they actually merge, if you have two black holes which merge, they settle down into a final black hole state and they kind of shake off any perturbations around them. That shaking off emits another burst of gravitational waves, which is called a ring down. So the final gravitational waveform that you get as a function of time, sort of the amplitude that you see, it looks like this. Okay, there's a frequency and then it increases, and then there's a ring down and you get something like this, which is decaying. Okay, so LIGO basically sees what is called a chirp. So as a function of time, you can also look at the frequencies, and the frequency increases with time till this point. So this spacing is getting closer together also. Okay, as I get closer to the merger. So this is the moment of merger. And then after this is the ring down, where it kind of settles down into a final black hole state. Okay, a single black hole and emits a burst of gravitational waves.
What is the order of the time for
This is few milliseconds. This entire burst is milliseconds.
for the biggest pulse? If it is one single pulse and we assume it having the speed of gravity or speed of light,
Yeah, this pulse.
then technically, if the length of your mass is small enough, then your light will not be able to travel the entire length while the gravitational wave is passing.
No, so the frequencies that we're looking in for these gravitational waves are such that they are much smaller than the source size. Indeed, what you're saying is right. It's kind of like a diffraction effect in that case. The wave optics effect of the gravitational wave would be important, but that's not the case here.
But for the pulse itself, is it like not a continuous rise, so that doesn't matter, or is it like one moment it really rises up?
No, it's pretty steady. I can show you these waveforms. It's fairly steady. Okay, it's not that sharp. Right. So you can measure all of this. The problem is in the detector you have lots of noise. Okay, so you have to see this above that noise. Okay, and one noise is short noise, but there are other sources of noise also, which you have to kind of eliminate. And sometimes, this I've drawn as a very prominent signal, but sometimes the signals look like there's noise, and then there's a little signal hiding here, and then there's noise. And how do you dig this out? Okay, so Professor Archana Pai in our department is involved in things like this. Okay, so it's called template fitting as one method to kind of extract these gravitational wave signals. Yeah. So the solution will show that it's retarded time. The reason is the gravitational wave takes time to propagate, right? So if there's a perturbation created at the source, you won't feel the effect instantaneously, right? It'll take a time r/c for that perturbation to reach you.
I don't understand why can't future merger not affect us?
Why can't a future merger affect us? Because that would be a wave traveling backwards in time. It's violates causality. Right. So when we're looking at the merger, this merger occurred a retarded time ago. So which means it occurred millions of years ago, right? Okay, I think let's stop here. Thanks.